Started. So I just have a few examples to go through today about non-homogeneous ODEs. So non-homogeneous ODEs, and then we're going to solve them using the undetermined coefficients method. So the first example I have is we're going to find the general solution of y double prime minus y equals e to the x. So if you remember that from what we did last time, so the first thing we have to do is we have to find the homogeneous solution by using the homogeneous equation y double prime minus y equals 0. And from there we can use the solution ansatz y equals e to the lambda x. Is it okay if I skip some work, just begin with the characteristic equation? So the characteristic equation, if we plug in the ansatz and the derivative, we get lambda squared minus 1 equals 0. If that's not clear to you, feel free to work out the steps on your own. So from there, when we solve for lambda, we get lambda equals plus minus 1. The base solutions is going to be e to the x and the e to the negative x. From there, we can write down the homogeneous solution, which is just a general solution to the homogeneous equation. That's going to be c1 e to the x plus c2 e to the minus x. Always remember that when you write down the homogeneous solution, there's c1 and c2 there. And then after this, we can guess the particular solution. And if you remember from last time, if we have f of x is e to the x, we probably want to guess the particular solution to be a e to the x, right? That's what we want to get, the particular solution, based on what we seen in the table from last time. Right? If you have an exponential function to be f of x, then we should try to guess particular solution to be a times e to the x. It turns out that because e to the x as a particular solution matches with e to the x in the homogeneous solution, so this, whatever the a is, a could be 5, a could be 1/2, whatever that is, that's already been included in the c1 e to the x. So even if you guess a y particular equals a e to the x, you're not going to get a value, because that's already involved in the, included in the c1 e to the x. So we don't guess this. Instead, we're going to take what we guessed, multiply by x. So a times x times e to the x. And then we're just going to multiply by x until we get something that's different from the homogeneous solution. So x e to the x is not in the homogeneous solution, so that's going to be a good guess. So let me write it down. If y particular matches with a term in homogeneous solution, we're just going to multiply the guess by x until it's different. So now we get a guess that's different from the terms in the homogeneous solution. We can find the derivative. So this is going to be the guess. And then we're going to find the y prime particular by using the product rule. So that's a times, if we use a product rule for x times e to the x, we should get 1 times e to the x plus x e to the x. That's a 1 times e to the x plus x times e to the x. You don't have to write the 1 there. Keep finding the derivative. So the second derivative of the particular solution is going to be a times e to the x, stays as e to the x when we differentiate, plus 1 times e to the x plus x e to the x using the product rule again. So that becomes a times 2e to the x plus x e to the x. And now we're just going to take those derivatives and the function, the particular solution we're going to put into the differential equation at the beginning. So we're going to take this derivatives and the particular solution we're going to put into the original differential equation. So that will become, so that's a 2e to the x plus x e to the x, and then this is the second derivative, and then minus y, so minus ax e to the x, and that's going to equal to the right-hand side e to the x. And then we just have to simplify this, try to solve for a. Going to expand the terms on the left, so that's a 2a e to the x plus ax e to the x minus ax e to the x. Excellent, because we get two terms will give us a 0 e to the x. So it turns out that that's going to give us a 0 when we have those two terms subtract. We just have 2a e to the x equals e to the x. I know that Professor Gibson show you that you can move e to the x to the left. You could move this to the left, having a 0 here, and the factor of e to the x, set the coefficient equals 0, right? That's one way. For me, I'm being a little bit lazy. I just look at them, like those two, like in my eyes, so I have e to the x, e to the x on both sides of the equation. Therefore, the coefficients, the terms in front of them must be the same. So that's 2a versus 1, so 2a must equal to 1. So 2a must equal to 1. A equals 1/2. This is just the way I do it. Again, you can follow either approach, whichever is convenient for you. So now we can write down the particular solution, which is 1/2 x e to the x, and the general solution, which is c1 e to the x plus c2 e to the negative x, and then the particular solution, 1/2 x e to the x. Any questions on that? It's always be careful after you find the terms in the homogeneous solution, you make the guess for the particular solution. Always check, make sure they're not the same. The next example I have, if you don't have any questions, I have y double prime minus 2y prime plus y equals e to the x. So go ahead and then take a couple of minutes to find the homogeneous solution, and if you are confident enough, move on to find the particular solution. I'm just going to write down what I have, and feel free to compare your work with mine. Any questions about finding the homogeneous solution? So when you find the lambda, it's a repeated roots, right? So that means when you write down the general solution for the homogeneous equation, you have e to the x by using lambda equal to 1. But then we have to multiply that e to the x by x. So the second term is c2x e to the x. Okay, so what about the particular solution? So we're going to guess y particular. So the first time you guess, you probably think, oh, we have e to the x. So we probably should guess a e to the x, perhaps. But it turns out that that's not going to be okay, because that e to the x matches with the first term in the homogeneous equation. So that's not a good guess. We're going to have to multiply that by x. So the second guess is probably a times x e to the x. And then you look at it, well, this one matches with the second term in the homogeneous equation, so that's also not going to be okay, because that, whatever that is, eventually is basically part of this term. So that's not a good guess. And then we're just going to keep going, multiply by another x. So we're going to guess y particular to be a x squared e to the x. And now it's different from the two terms. So we're going to use this. And the rest is similar to what we had before. We have to find the derivatives, put in there. So y prime p, use product rule. So I'm going to leave the a aside. When I differentiate, I don't touch the constant. So if I put away the a aside, so look at x squared e to the x. When I differentiate, x squared gives me 2x. So that'll be 2x e to the x plus x squared times e to the x. So that's the first derivative, and then take the derivative again. Again, I'm going to leave the a aside, don't worry about it. When you take the derivative again, there's a couple of tricks. You could leave the 2 aside, only works on x e to the x if you want. Or you can just leave it with 2x together, doesn't really matter. So 2x derivative is 2. So that will be 2 times e to the x plus 2x times the derivative of e to the x is e to the x. And then we have to work with the x squared e to the x. So that will give me 2x e to the x plus x squared e to the x. We can simplify a bit by combining the middle terms, give us 4x e to the x. I'm going to be lazy here, so instead of rewriting the second derivative, I just leave it the way it is, but when I use the second derivative, I'm going to use 4x e to the x. So that will be, now we're going to take everything, put into that differential equation. So we have a times 2e to the x plus 4x e to the x plus x squared e to the x. So that's the second derivative minus 2 times the first derivative. So 2 times a 2x e to the x, and then plus x squared e to the x. That's the first derivative term, and then we're going to add a y term, which is a x squared e to the x. And that should equal to e to the x. And then the next thing I'm going to do is I'm going to expand to the left side completely. And in the following step, I'm going to group the terms with the same function of x. So that will be 2a e to the x plus 4ax e to the x plus ax squared e to the x minus 2a times 2x, that's a 4ax e to the x. And then 2a times x squared, so that's a minus 2ax squared e to the x plus ax squared e to the x equals e to the x. But just by inspection, it's really nice. And in fact, this is something you could kind of, don't have to memorize it, just something to think about. If we only have one undetermined coefficient a in this example, if we have a lot of terms at the end, that means quite a few terms that will cancel because we're probably not going to use all of them to find a. So it turns out that by just looking at it, we have 4a positive 4ax e to the x, then we have minus 4ax e to the x, so that goes away. Then we have ax squared, well, 1 positive 1a, then we have minus 2ax squared e to the x, then we have positive 1ax squared. So lots of the terms will give us a 0 when we add them. So that's going to give us a 0. This term in the middle, and then those last two terms. When we add all of them together, we get 0. Again, we have 2a e to the x equals e to the x. So we have a equals half. So we can write down the particular solution, which is x squared e to the x times 1/2, and then the general solution is just going to be c1 e to the x plus c2 x e to the x plus c3 x squared e to the x times 1/2. Oops, I made a mistake, not c3, 1/2. Sorry, that's a particular solution. Any questions about this example? Again, this example is similar to what we had the first one. Basically, when you guess the particular solution, always check, make sure it's not matching with the terms in the homogeneous solution. If it is, just keep multiplying by x. All right, the next example I have is y double prime plus 2y equals e to the 2x plus x cubed. So I'm going to start writing down the homogeneous solution part. So that's going to be, so to solve y homogeneous, we have y double prime plus 2y equals 0. The characteristic equation is lambda squared plus 2 equals 0. And the lambda turns out to be complex. So that's going to be plus minus square root of 2I, right? So here, when we write down the homogeneous solution, we could use e to the base solutions. We could write e to the square root of ix and the e to the negative square root of ix. That's one way. But we could just use sine and cosine, right? And in fact, sine and cosine sometimes is easier to find, easier to use if we have initial conditions. So cosine square root of x, square root of 2x, and the sine square root of 2x. We're just going to keep positive for both. You don't have to put a negative sign in any of in either cosine or sine. And even if you do have a negative, it's not wrong. It's just that the negative will be absorbed into by C1 or C2 at some point. So it's nothing wrong there. So we're going to use sine and cosine. The homogeneous solution is going to be C1 cosine square root of 2x plus C2 sine square root of 2x. And then the next step is to guess the particular solution. Well, be a little bit careful here, because here we have e to the 2x plus x cubed. It's a sum of two functions of x. So if we just have e to the 2x, we're going to guess the particular solution to be a e to the 2x, right? But if we just have x cubed, it's not going to be ax cubed. That's not going to be correct. For cubic terms, x cubed, we have to include all the terms after x cubed. So we have to include the x squared term, and then linear term, and also the constant. We just have to consider all of those when we find the particular solution, when we guess the particular solution. So at the end, if I put them together, I don't want to have two a's, so I'm going to change the coefficient for e to the 2x to maybe, I don't know, what's the next good letter for that? Maybe A1 or F or G. I don't like to use E there. There's nothing wrong with using E. It's just that we have a base E. So maybe we can use J e to the 2x plus ax cubed plus bx squared plus cx plus d. You can pretty much pick any representation for the coefficients. And now we can find the derivatives. Y prime p, if we take the derivative of the first term, we get 2j e to the 2x, the 2 coming from the chain rule, and then plus 3a e to x squared plus 2bx plus c. Take the derivative again. We should get 4. So 4j e to the 2x plus 6ax plus 2b. There's no c when we take the derivative. So this number increases because of the chain rule. When we take the derivative of e to the 2x, we get e to the 2x times this 2 each time. And now we can take those, put into the differential equation. So we get second derivative, so that's a 4j e to the 2x plus 6ax plus 2b. And then we have plus 2 times the y, so that's going to be j e to the 2x plus ax cubed plus bx squared plus cx plus d. So it's very important you keep track of all the terms you wrote. Don't forget anything or write them incorrectly when you plug them in. And that's going to equal to e to the 2x plus x cubed. Maybe I should solve the rest of the problem by using the way that Professor Gibson does. Is that going to be helpful? By moving the term from the right to the left? Any preference? No? All right, so I'm going to try to solve what Professor Gibson does by moving those terms to the left and then combine with the terms there. So what do I have is, I'm going to first expand the bracket. And then I'm going to move those two terms to the left, and now should have a 0 on the right-hand side. So I have 4j e to the 2x minus plus 6ax plus 2b plus 2j e to the 2x plus 2a x cubed plus 2b x squared plus 2cx plus 2d. And then when I move the terms to the left, I should have negative sign, so that's minus e to the 2x minus x cubed equals 0. And then now I'm going to combine like terms. So all the terms with e to the 2x, I'm going to group them together. So that will give me those terms should be grouped together. So that will give me 4j plus 2j, that's a 6j, and then minus 1 times e to the 2x. Then I have all the terms with x cubed, which is really just two terms with x cubed. So that will give me 2a minus 1 x cubed. And all the terms with x squared, there's only one term with x squared, which is 2b x squared, nothing else. And then all the terms with x, I'm going to put them together, so I get 6ax. Then I have 2cx, so I have 6a plus 2c times x. And at the end, all the terms that doesn't have any x, the constant terms, I'm going to put them together. So I have 2b and the 2d. So 2b plus 2d, group them together. That's it, right? That's all the terms on the left, so that should equal to 0. Okay, so at the end, because we have a 0 on the right-hand side, On the left side, we have various functions of x adding together. If we want a 0 on the right-hand side, we have to make sure that all the coefficients on the left side equal 0. Because for x equals any number, that's the only case we're going to have a 0 on the right-hand side. So we have 6j from the first parentheses minus 1 must equal to 0. 2a minus 1 must equal to 0. 2b also has to be 0. 6a plus 2c equals 0. 2b plus 2d also has to be 0. Which is good, right? Because we had five unknown constants to begin with. And at the end we have 5 equations. That should be enough to solve every one of them. So that gives us j equals 1/6, a equals 1/2, b equals 0, c equals negative 3/2, d equals 0. You can double check but those are the coefficients I got. Any questions? So now we have those coefficients. We can write down the particular solution. So yp. So we can take this a, b, c, d, j. We can put into the particular solution we guessed. So that's going to be, this is the particular solution we guessed. Oops. We guessed earlier. So if we put in this coefficients, we get 1/6 e to the 2x plus 1/2 x cubed plus 0 times x squared. I'm not going to write down that 0. And then plus c times x, so that's a minus 3/2 times x. And then plus d, which is a 0 again. So this is the particular solution. And then we can write down the general solution, which is, if you recall, the homogeneous solution is c1 cosine square root of 2x plus c2 sine square root of 2x. And now we're going to add the particular solution, which is 1/6 e to the 2x plus 1/2 x cubed plus 3/2 x minus 3/2 x. Any questions about this problem? You guys are awfully quiet. I hope it makes sense. Okay, good. So that's the case when you have a sum of two different functions on the right-hand side. You just find the corresponding particular solution for one of them, and then the other one you add them to be the particular solution. But remember that if you just have x cubed, doesn't mean there's no x squared or x all constant in the final particular solution. So that's why we have to include all of them when you make the guess. All right, last example here. Y double prime minus 4y prime minus 12y equals 5x e to the 4x. I'm going to write down the homogeneous solution because we did that last time. So y homogeneous is going to be c1 e to the 6x plus c2 e to the negative 2x. And then let's just find the particular solution directly. So as you're writing down the problem, think about what the particular solution should be in this case. So the function on the right-hand side is 5x e to the 4x. 5, obviously, we don't have to worry about the 5 because it's just coefficient there. And then we have x e to the 4x. Does that mean we're just going to add a constant a in front of it to be the particular solution? Well, that's not really a x e to the 4x is really not a function in the table I gave you last time, right? So you have to be a little bit more careful here because this part is actually a product of two different functions, the linear function x, or 5x, and also the exponential function. So this is the product of 5x and e to the 4x. Which means when we guess a particular solution, we have to use a product of corresponding particular solutions from here. The 5x will give us ax plus b as a particular solution. The e to the 4x will give us a e to the 4x. Obviously, I'm using a again. We don't have to use a. We can use c or b, doesn't matter. So we're going to have to take those two particular solutions, multiply them together to be the guess. So that will be ax plus b times a, oh not a, I'm going to have to use c, e to the 4x. So that will be the guess, the product of the corresponding particular solution. And of course, if we look at it, it's like, oh, there's 3 coefficients, right? We have A, B, and C. Is that really necessary to keep all 3 coefficients? The answer is no. Because the C there, we can distribute into the parentheses and rewrite it as ACX plus BC times e to the 4x. It turns out that A and the C are constants. If you multiply them, you still get constants. B and the C are constants, which means we can rename them. Maybe we can call it alpha x plus beta e to the 4x. That way, instead of working with 3 coefficients, A, B, C, we really just have 2 coefficients, alpha and the beta. We don't have 3. So we just need to know those 2 numbers. So that's something that you can keep in mind. And now we're going to find the derivative and then put in there. I'm going to do it a little bit quick here because it's product rule, right? So that's going to be alpha. Is it okay if I use alpha and beta, or do you prefer something else? Fine? Okay. So it's just going to be alpha times e to the 4x plus alpha x plus beta times e to the 4x times the 4, using chain rule there. Well, product rule and then chain rule. And then let's take the derivative again, which is going to be 4 alpha e to the 4x plus 4 times product rule one more time. So that's going to be alpha e to the 4x plus 4 times alpha x plus beta times e to the 4x. From here, there's a couple of things we could do. We could fully expand every term there if we put it to the differential equation, or we can just leave it, or we can simplify it kind of halfway. What I'm going to do is I'm going to distribute the 4 into the bracket, but not expanding the parentheses. There's no particular reason to do it, it just seems to be a little bit easier without actually doing all the expansion. So 4 alpha e to the 4x plus 4 alpha e to the 4x. So that together give me 8 plus 16 alpha x plus beta e to the 4x. So I'm going to rewrite this first two term as 8 alpha e to the 4x. And then now I'm going to take the derivatives, put into the equation, so I get, so if you recall that that's what the differential equation looked like. The second derivative minus 4y prime minus 12y equals this. So if I put in there, we get second derivative, 8 alpha e to the 4x plus 16 alpha x plus beta e to the 4x. So this is the second derivative part. And then we're going to minus 4 times the first derivative, so 4 times alpha e to the 4x plus 4 parentheses alpha x plus beta e to the 4x. So this is a y prime, so we get minus 4y prime of the particular solution. And then we're going to minus 12y, which is y is 12 times alpha x plus beta e to the 4x. So this is the y particular. And then eventually all of this is going to equal to 5x e to the 4x. And then the rest is about simplifying. There's kind of like, for me, if I need to simplify anything, to cancel out some of the terms or to combine like terms, I don't just, jump in and expand everything completely. I kind of just look at them, see if there's any easy parts that can be canceled. For example, by just looking at them, looking at those terms. So here, I have 16 times parentheses e to the 4x. But then I look at this, I have minus 4, then I have positive 4 parentheses e to the 4x. Looks like that's going to be a negative 16 times the parentheses times e to the 4x. So instead of fully expanding it in the first place, I kind of just expand it halfway. So that will give me 8 alpha e to the 4x plus 16 alpha x plus beta e to the 4x minus 4 alpha e to the 4x minus 16 parentheses alpha x plus beta e to the 4x minus 12 alpha x plus beta e to the 4x equals 5x e to the 4x. And if you prefer to expand everything completely, that's perfectly fine. It's just that for me, it's like, oh, looks like we can save a little bit, energy on this part, because that and this term give me a 0. Those are just small little tricks. It doesn't really make a huge difference, but it's kind of saves a bit more time, I suppose. And then what do we have? We have 8 alpha minus 4 alpha. That's a 4 alpha e to the 4x. When we combine those two terms. And then what about the rest? Well, the rest actually I don't need the parentheses, so I can expand that last term on the left. So that's a minus 12 alpha x e to the 4x minus 12 beta e to the 4x. And then you can keep it on the right hand side, or you can move it to the left. It's really up to you. I guess for practice, maybe I'll move it to the left. So that's a minus 5x e to the 4x equals 0. just to be consistent with Professor Gibson's notes. And then we're just going to have to combine like terms from here. So I have e to the 4x, e to the 4x. I'm going to put those two terms together. So I get 4 alpha minus 12 beta e to the 4x. And then I have minus 12 alpha x e to the 4x minus 5x e to the 4x. So that's I'm going to use a positive sign. So minus 12 alpha minus 5 x e to the x equals 0. And this is like what we did before, right? If we have the right-hand side equals 0, and then this equation is only true for any x if the two parentheses become 0. So we get 4 alpha minus 12 beta equals 0. Negative 12 alpha minus 5 equals 0. We can solve for alpha, which is negative 5 over 12. Beta, I don't know what beta is. I'm just going to leave it for you to find out. So, negative 5 over 3 divided by 12. Negative 5 over 36, I think. Double check. This is the, no. So now we have alpha and a beta. So what we do is we're just going to write down the particular solution. Remember that the particular solution at some point was in terms of alpha and beta, right? So if you look back, that's a particular solution. We don't need to find ABC. In fact, we can't find ABC. Just use alpha and beta at the end. So that's going to be negative 5 over 12x minus 5 over 36 e to the 4x. That's a particular solution, and we can write down the general solution by adding the homogeneous to the particular. Questions? All right, to finish 2 minutes early, and I'll let you go and enjoy your break. Stay healthy, and I'll see you the Tuesday. All right, take care, everyone.